Okay, so I'm going to talk about some of our recent results with my wonderful collaborators on the statistical complexity of reinforcement learning. Okay, so I would assume that RL has been introduced many times already today, so I'm going to skip the non-technical stuff very quickly. So basically, we are all very familiar with all the phenomenon successes of reinforcement learning and deep reinforcement learning. But we are here for this workshop because we are theoreticians and we want to understand theoretically why this is true and what can we say about reinforcement learning from optimization perspectives and from control perspectives. So I want to talk about several very basic statistical questions about reinforcement learning, especially about reinforcement learning when we have limited accessibility to data. Okay, so the first very basic question is the following. I believe maybe Chaba already mentioned something about this. So the first very basic question is, let's suppose that we have a perfect generator of the reinforcement learning problem. By that, we mean that we have a generative model, or like a perfect simulator of the environment. So we, as the user, we are allowed to specify any initial state and action. And then this generative model is going to return to me a random state and a random reward at that state action. Okay? So this generator should be sufficient for us to learn about the environment, even though we do not know its full transition dynamics. And then our basic question is, how many samples are sufficient and necessary to get a good approximate optimal policy?
What's the difference between a generative model and a state space model?
I don't know what is a state space model.
It's probably a generative model.
Okay, yeah. Sounds good. That's good to know. So the notion of generative model comes from Sham Kakati's thesis, and I'm just borrowing his terminology. And it's good to know that there is a nice terminology I can use in the control literature. Thank you very much. Okay, so we want to understand what is the necessary and sufficient sample size to get a good policy, or maybe a 90% optimal policy, or an absolute optimal policy. Okay, and this is just a page of notation. Let's start with the very basic setting in which we have a finite state, finite action Markov decision process. So we have a reward function, which is really, in this case, a long vector. So we have a reward for each state and action. And we have a set of transition probabilities defined over the state action space. And the optimization problem is we want to find one policy, which is a mapping from the state space to the action space. And then we want to maximize the cumulative sum of rewards generated by this policy. I think in the CS literature, sometimes this problem is called tabular MDP, meaning that really we can represent all the information about the model in a table. And also by tabular, we mean that if I have one state and I have another state, what I learn from state A does not tell us anything about state B. So there's no geometry in the state space. So that's the tabular case with no structure. Okay, so even for this very basic question, if we want to get an absolute optimal policy, it turns out that the known sample complexity using variance of value iteration or empirical value iteration, so even the known sample complexities actually were not really close to optimal in the earlier attempts. So you can see that there's a line of improvement, and most of the improvement is really on this exponent, whether it's 1 minus gamma to the 7 or 1 minus gamma to the 3. So you might question why this is important. It's polynomial, right? And we're happy. But if you think about it, this is about a discounted problem, and gamma is usually taken to be 0.99. And this 1 minus gamma factor is really like the effective horizon of the process. And then if we look at a typical value of gamma, the improvement from the power of 7 to the power of 3 is really 10 to the 8 times, which is a huge multiplicative factor in the sample size. So the best known results for the tabular MDP are the following. So again, under this generative model, which is a very nice assumption to have, under this generative model, and the information threshold limit and the sample complexity of the best known algorithms now basically match with each other. So actually there are actually multiple algorithms now to achieve an absolute optimal policy using this sample size. And this sample size is actually not improvable, and there was an information theoretical lower bound proved a few years ago. Okay, so now basically the first question, sample complexity for learning a good policy for tabular MDP under this nice generative model, this question is already answered. Okay? So now we want to ask harder questions. So one thing we're not happy is S, which is our state space. S is something too big to be reasonable. So we all know, everyone knows about the curse of dimensionality, right? So if I want to do a plane discretization of a continuous state space, then the number of states is exponential in the dimension. And the number of policies is actually even more exponential. And even if we take the logarithm of the policy space, the log of the policy space is actually another exponential number. So this basically says that, well, it's nice to have those nice upper and lower bounds. It's nice that they match, but those results are not good enough for us to really understand what's happening with problems with large S. Okay. So now let's add some structure. So what if we have features? So having state features is actually a common practice which were used by game solvers long before deep reinforcement learning. So I believe like researchers in the 1980s, 1990s, they were already using feature representation, linear model approximation, and the tree search to approximately solve games. And to my best knowledge, I think the first computer game to be solved by ADP was, is that Backgamma or Tetris? Backgamma. Okay. Yeah, and also like for a game like Tetris, this game can be well solved way before deep learning. Okay, so what do we mean by having a state feature map? We mean that if we have a raw state, we can map it to a number of feature values. For a very simple example, like in the 1990s, people can solve Tetris by just using hand-picked features. And the hand-picked features can be just this height, or some structures about the frontal level, or just something that makes sense to the player. And for a more modern example, the feature map can be simply the neural network representation, the last layer neural network embedding learned by any network we are having. And for a third example, we can think about the phi to be an even higher dimensional vector, and we can achieve this by starting with a kernel space and doing random feature generation to lift the dimensionality to get a better but closer to linear structure. Okay. So what can we do with a state feature map? Again, returning to this very simple example of Tetris. So what we can do is, okay, so in order to deal with curse of dimensionality without doing any theory yet, basically what we want to do is we always want to approximately represent high dimensional functions using lower dimensional representations. And in this case, we can try to represent the value function, which could be a huge vector whose dimension equals the total number of states. Can we represent the high dimensional value function approximately using a linear combination? Okay. And one can do it very simply in Tetris by just having a number of weights for each feature and try to use it as a heuristic or as a proxy to the actual value. Okay. And the linear function approximation has a lot of other issues, like what happens with model misspecification, and I believe Chaba already told you about the recent progress. So I think the short message is having approximate linear representation is actually very efficient. Okay. So to really think about the theory of solving Bellman equation in using feature representation, let's look at the Bellman equation. So the Bellman equation is a set of variational inequalities, or is a set of fixed point nonlinear equations. But however, if we look at this, so this is the average reward Bellman equation. So I don't have discount factor here, but we have a constant shape for average reward. Okay. So in this case, we basically have one max, this red max here, for every state and for every action. So we want to achieve optimality for every state. So somehow this nonlinearity makes solving Bellman equation hard, because it's hard to do function approximation and nice parameterization when we have a high-dimensional nonlinear system of equations. And then I suggest that maybe we can look at Bellman equation from an alternative way. So I believe many of you are familiar with the linear programming formulation of Bellman equation. I don't know, are you?
I totally believe.
Oh, okay, awesome. So the Bellman equation, which is equivalent to a linear program, a high-dimensional or even infinite-dimensional linear program, is also equivalent to a minimax problem. And this is actually a bilinear minimax problem. So one way to think about dimension reduction of Bellman equation is we can think about that we have a minimax problem involving high-dimensional value functions and a dual variable, which is a high-dimensional stationary state action distribution. So both of them are high-dimensional functions. But it's possible that we try to exploit lower dimensional structures in this minimax problem. Okay? Okay, so one way to think about this is we can always start with the original Bellman equation, high-dimensional but nonlinear, which is equivalent to a minimax problem over high-dimensional value functions and high-dimensional state action distributions. And however, now we can borrow ideas from empirical risk minimization from statistic learning, right? Whenever we want to estimate a high-dimensional prediction function, we can try to search for it within a nice known function class. By using this idea, we can think about this high-dimensional saddle point problem as maybe we have nice function class for the value function and the state action measure. And if my function classes happen to be linear spaces, then the Bellman equation becomes a lower dimensional minimax problem. And we can use tools from optimization to solve it. Okay. So, so basically, by using this intuition that we can approximately solve high-dimensional minimax problem over nice function classes, one can find an approximate optimal policy, now using a sample size that is linear in the number of state features times the number of action features. Okay. And we also had a result for the discounted case, which is actually Minimax-optimal. Okay, so now if you think about it, it's actually not very surprising. Originally, we have a huge LP, a huge linear program, S times A times S. And now if we know that all the variables we care about live in the low-dimensional spaces, this giant linear program becomes something smaller, and the complexity reduces accordingly. So this is very intuitive. Okay. So now let's move on. So
can I just ask Mengdi on the previous slide? I noticed that you don't have the. I'm a complete outsider, but I noticed you don't have the mixing terms in the discounting case. Is that because they're dominated by the discounting term, or it's just not so much a consideration?
The mixing time usually only shows up in the average reward problems because it's sort of, again, like an effective horizon. And in the corresponding discounted problem, the mixing time just can be bounded by 1 over 1 minus gamma. So basically, we're happy with just considering this long, and we can forget about the rest. Okay, so now let's try to relax our assumptions a little bit. So we were assuming that we were assuming that we had this nice genuine model or state space model, which basically says that we have to be able to learn about the system dynamics as long as we are happy to keep generating samples. But now let's make the problem a bit harder and more realistic. So what if we have to only rely on what we have observed so far? So what if we have past experiences and we want to use the past experiences to our best? So this is usually called batch RL or off-policy reinforcement learning. So let's consider like problems from, for example, from the medical domain. For example, we want to learn from clinical data. What if I want to try a new treatment policy? How does the new treatment policy perform? Can I predict its performance based on past patients' data? Or make it even harder, if we want to do experimental design, and we only have very limited data we have collected from those mouse. And can we use this limited data to predict something about what could happen if I try a different experiment? And in clinical trials, each data point could be one human being. So this is the kind of problems in which it's difficult to simulate. And collecting data is going to be very costly. And now we ask the same question. What is the statistical limit for this problem?
So this represents each 7 pills. There are 7 different kinds of pills or whatever. The 3, and then you have to pick between 2 and so forth. Is that the idea?
No, this figure is what I borrowed from the internet. It's not mine. I don't actually know what it represents. Yeah, I think they are just like keeping candidates and trying to bow down to the last one, and they are going to scale up their experiments. Yeah. Okay, so now let's define the problem. Okay, so this problem is called off-policy policy evaluation. So by that, we mean that suppose that we have a data set. I'm going to call it D. In the data set, I have a collection of state action, state reward transitions. The data could be generated from some expert policy or some non-expert policy. But we do not know what is the policy that generated the data. But I only observe the transitions. Okay. And my goal is, let's consider a simple goal for now. Let's say that I have a new policy. Let's call it the target policy pi. And our goal is to simply evaluate the performance of the new policy pi from a fixed initial distribution. And I'm going to call this cumulative reward as V pi. So this question is very well defined. I have a data set, and I want to estimate one single value, which is the value of a new target policy pi. Okay, so this is not about learning the optimal policy yet. But if you think about it, this is actually a very basic but first-order question to ask. Because, for example, if we have a good algorithm that can effectively evaluate all the policies, then basically we are done. I just look at all the policies, and then I evaluate them, and then we just pick the best. Right? If that could happen, then we are done. Okay. And however, in typical settings, things are not so simple. It could be that there are certain policies we can evaluate because my data can represent this new policy. And there could be other policies which I just cannot evaluate because my data does not support it. Okay, so being able to evaluate one new target policy is important because it can enable downstream tasks. I should be able to tell how much I can evaluate each possible new policy and how and where shall I explore next.
What do you mean by first order tasks?
By first order tasks, I mean it's like a first question to ask. And for example, if we want to find the best policy, could be a secondary thing, because finding a best policy relies on being able to solve this problem.
So do you mean by that an initial guess? An initial set of data? I don't.
It's criticality. It's first
what?
order. It's first order critical. It's the most critical task. That's what.
Oh, okay. All right.
Yeah, thank you, Chaba.
You're going to put on different tasks. Okay. Thank you.
Okay, so now we have this very basic question. Given a data set, estimate one value. Okay, so I don't know how much you have followed the literature of policy evaluation. So there are a lot of methods rely on importance sampling. So to give you a basic idea, it means that, okay, I have sample transitions from one policy, and I want to evaluate the mean of reward under a new policy. Then it's like I have samples from one distribution, and I want to evaluate the mean over another distribution. So naturally, one can think about importance sampling. And then for a very basic question is, okay, for example, I want to estimate the one-step reward under a policy pi, starting from a state S. Okay, and suppose that I know the two policies. Say that the two policies could be randomized policies. Okay, and then I can simply look at all the related reward samples, and I can reweight them by multiplying them with the ratio between probabilities for the actions to be chosen by the two policies. Right, this is really just importance sampling. Okay, and to do this for RL is challenging because what I do right now is going to affect the distribution of state in the next time step. So there are variants of importance sampling that actually require estimating the density ratio, which is the density ratio between the long-term state action occupancy measure under the target policy versus the long-term measure under the data under the generating policy. Okay, and there are a lot of works, and maybe you can check out some of those papers. So what's not good with this? So this is a very natural first thing to think about it. But if we think about importance sampling, we all know that to make importance sampling work, we really need a lot of data points, right? To evaluate one single reward function, we need to take this ratio, and this ratio could be extremely large. And if we roll it out to do multi-time step policy evaluation, then what could happen is we can get huge error bounds in the tabular case without any prior knowledge about structures of the MDP. Okay, and also there's this notion of curse of horizon. Basically means that I have one policy, data from one policy, and I have another policy. So the policy evaluation error is going to grow exponentially as the horizon grows. Because if I have some error in the first phase, and then the next phase, my error could accumulate in a multiplicative way, so which could happen. And as a result, many algorithms like TD learning could easily diverge. Okay. So now I'm going to propose one solution. And the solution is actually very simple. So I'm going to use a function class. I'm going to call it function class Q to represent Q functions that we care about. And to make function approximation work exactly, we're going to need a bit of assumption. Let's say that p pi is the transition operator under the target policy. Now suppose that we want to make a function class Q to work. And I'm going to assume that this function class is sufficiently expressive. By that, I mean that the transition operator that we care about is closed in this function class Q. Or in other words, I mean that if I apply p pi to some function f in this function class, the result also belongs to the same function class. Okay, so if this assumption doesn't hold, then basically it means that this function class is not expressive enough to represent what happens in one-step transition. And we're going to assume that we have a function class to be able to represent the one-time step transition. Okay, so let's say that we already have this. And now I'm simply going to estimate all the Q functions by regression. So we start with the ending Q. We just made it 0. And now whenever we want to do Q iteration, we simply do a regression with the regression target being the expected next state action value. And the expectation is taken over the target policy, which we know. Okay? And this regression is done by just doing least square over all the data we have. And then what happens is we're simply doing least square supervised learning, and we roll it out for h time steps or for enough time steps. And hopefully we get something that's reasonable. And finally, we can evaluate the initial value of the policy and the initial distribution. OK. So this still looks complicated. This particular method is just a direct regression approach. Sometimes it's called fitted Q iteration or fitted Q evaluation. OK, to make it even simpler, so what I just described is nothing more than a plug-in estimator. OK, so what is this plug-in estimator? Again, we have a bunch of data points, right? Each data point is one sample transition. And we're going to do regression over this data point, over all the data we have, to define an empirical p-hat. And this p-hat is basically by doing supervised learning to approximate the best transition operator within the function class we have. OK, we can also estimate r-hat, the instant reward function, by just doing regression. OK, and now we have an empirical transition operator and an empirical reward. So we have another empirical problem. We just solve it. So that's why I call it a plug-in estimator. We estimate the model, and then we solve the model to evaluate the policy. So this is very straightforward. And one can actually show that when the row function, this penalty function, is taken appropriately, the regression-based fitted Q iteration is equivalent to a plug-in estimator. OK. And one can also verify what does the empirical transition kernel looks like when the Q function class happens to be a linear function class. So this is actually a standard form of conditional mean embedding. OK. So now we have a method. This method is about using regression to estimate the MDP model and then solve it. And since it's a plug-in estimator, as long as we have a way to estimate the model, or by estimate the model is we can simply build a model predictor and then use it to do model predictive control. That's also a plug-in estimator. And then we can either use Q iteration or we can use other methods to solve it. We can solve plug-in estimator basically using any existing algorithm. OK. And now what can we prove about it? So one can show that this plug-in estimator, which seems very straightforward, this plug-in estimator is actually statistically optimal. So by that, I mean that if we look at the policy evaluation error, the difference between v hat and v, this error is bounded by a complicated formula, which I simplified to look like this. OK? So there's an upper bound that can be proved. And on top of this, one can actually show that this upper bound is actually non-improvable, meaning that across all estimators, all algorithms, we can always find some hard problem instances such that no matter what algorithm we use, the policy evaluation error is at least this much. So basically, one can prove an upper bound and a lower bound, and again, they match. And there's a term here which I found interesting to share about. So this term, I call it chi-q square, which is defined in this way as in a variational way, and it's defined over this function class Q. OK. And let's say that is a notion of divergence between two distributions. One distribution, mu bar, is a weighted occupancy measure under a target policy. The other distribution, mu bar, is the distribution, I would say the state action occupancy measure associated with the data that we have. So really it's about some divergence between the two distributions. One is data, the other one is target. Okay. So I think the short message is actually regression and plugin estimator is pretty good enough for predicting performance of new policy from batch data. Okay. So a bit more on this chi-q square. So it is actually a variant of chi-square divergence. And it's a notion of chi-square divergence restricted to the Q function class. So for example, in the tabular case, recall in the tabular case, we have no structure. So I mean that the Q function class is the entire space. In this case, this Q chi-square divergence reduces to the plain Pearson chi-square divergence. Okay, but the chi-square divergence between two distributions could be large because we're measuring the divergence basically between every potential element. And now if I take my Q function class to be a linear subspace, so if I have more structures about the Q function class, what happens is the Q chi-square divergence between two distributions can be bounded from above by a relative condition number, which measures the mismatch between covariance matrix under P1 and the covariance matrix under P2. So you can see that because now we have a function class, this restricted chi-square divergence could be much smaller than the plain chi-square divergence. We can characterize using condition numbers. Okay, so basically this divergence characterizes the mismatch between two distributions over a function class. Okay, and if the function class is small, it basically means that the function class can help us to generalize what we have seen in the data to predict new policy's value. And this chi-square divergence doesn't have to be huge. Okay. So I don't know if you guys want to learn about the lower bound analysis, because the upper bound analysis is just analysis and concentration and the keep doing analysis. But lower bound analysis is actually fun. Okay, so in case you're interested, I'll try to explain the basic idea. So whenever we try to prove that this is an error lower bound, we mean that we want to construct problem instances that are similar, that are hard to distinguish, but one has to still make an error on one of them. So I'm going to start with one transition kernel P, and I want to perturb it to get a similar instance P tilde. So I'm going to perturb it in such a way. So phi is the feature space we're working with. Okay, and this Q is something I have already constructed. So my goal here is to construct a vector x. You can think about this as a direction of perturbation. I want to perturb one MDP to get another one, and I want to choose a direction to perturb it. The direction is x, which is a vector. And let's do a likelihood test. So given the data set, so I have a data set, right? So we're going to compare the likelihood for generating this data under the first model and the likelihood for generating the data under the second model. And then we compare their likelihood. So this is a likelihood ratio test. And one can show that this likelihood ratio actually concentrates to a quantity that is determined by the perturbation direction x. So if x is 0, the two instances are similar, and the likelihood test is the log likelihood will always be 0. So basically, once we are here, we can show that as long as the perturbation is small enough, so if the two models are very similar, then this likelihood is going to be large with high probability, which means that the two instances appear very similar to us based on the data. We cannot tell which is which simply from the data. Okay, and it also implies that we have to make some mistake on one of the model. And finally, we try to calculate the gap in the policy values between the two different MDP instances. And we can quantify this gap, again, as a function of x. And finally, in order to prove the sharpest lower bound, we want to maximize the gap in the values under the constraint that the two models are still very similar. And the constraint is the constraint here to make the likelihood ratio large with high probability. And by that, we can find the best perturbation direction. So we can find a similar instance, which is still similar, but has the largest difference in policy value. And putting them together, we can show that actually we have to make some mistake on one of the model. And the mistake is the lower bound I just presented. OK. Again, so if there's one message that's worth noting here, the message is actually regression is good enough for off-policy RL. And finally, I think I have like maybe 10 minutes. So one might ask, OK, can we just make our lives a bit even more difficult? What if we want to do online learning? I'm not learning from a fixed batch data. I want to learn to explore adaptively. Can we do adaptive control? And the question is, we knew regression works in the offline setting. Does regression also work in the online setting? OK. So in this case, we no longer have generative model, which is too perfect. And we no longer have batch data. We actually want to learn from the scratch. And we consider the episodic learning setting, in which the controller has to always start from a fixed initial state. It has to learn episode by episode. And let's say each episode has h time steps. OK. And by nature of the problem, the controller is not guaranteed to visit all the state space. But we still want to have a notion of efficiency in learning. And in this case, learning theoreticians care about the regret of a learning algorithm, meaning that I have a controller which starts adapting across a number of episodes. I'm going to calculate all the rewards earned by this controller. And then I'm going to compare this value with the optimal value that can be earned by the optimal controller. And we call this value the regret. OK. And the problem is there's a lot of dependency in the data, and the algorithm has to self-adapt. OK. Let me try to go a bit quickly.
Small question. How do you know the optimal controller?
We do not know. It's like it's like when we prove convergence to the optimal solution in optimization problem. We do not know the optimal solution, but we want to know some bound, some error bound. So in this case, we do not know the optimal controller, but we want to have an error upper bound for the regret. OK. And again, I'm going to do it in a regression manner. OK. Again, suppose that we have state action features and state only features. So I'm going to have a phi vector representing state and action pairs, and I have a percent vector to represent the next state. Now let's do regression and model predictive control. The assumption is actually there exists an optimal predictor such that given the current state action features, and there is a linear model to predict the expected next state in its feature form. OK? So it means that we are trying to look for a predictor to use the current state action to predict functions of the next state. OK, and this, again, is a regression problem. And M star is a core matrix, can be a huge matrix if I have a large number of bases, and we do not know this M star. OK. And now we are going to do basically regression together with exploration. So the basic idea is whenever, at any time point during the learning process, we must have already collected a bunch of sample transitions. So we're going to do regression over the sample transitions to estimate this prediction model, in particular to estimate that core matrix M. And around our estimated M, we're going to construct a confidence ball based on the data we have. And then based on that, we're going to use the confidence ball of estimated models to plan optimistically what should be the next policy I'm going to try in the new episode. And as I learn, this confidence ball should shrink as I collect more and more data, and my policies will be adapted according to the current confidence ball. So we keep doing this. Okay, but the key is using regression to predict the model, and then I build a confidence ball around the regression estimate. Okay, and this algorithm we can hide this confidence ball and write it in a more explicit way in which every Q iteration is actually a regression. So let's get to this quickly. Okay. So one can do some regret analysis. Recall the regret is going to be the actual performance compared to the optimal performance. And one can show that this regret is bounded by a function of the order square root of t. And also this regret depends linearly on dimension of the transition model, because we are basically estimating transition model. And also what's interesting is the method I described can be extended to work with basically any reproducing kernel Hilbert spaces. So if we do not have the nice feature functions we begin with, instead, if you give me a nice kernel function over the state space and and another nice kernel function over the action space, we can actually do this matrix regression RL algorithm in a kernelized way. And in this case, the regret depends on the Hilbert Smith norm of the transition operator. Okay, and some effective dimension. Okay, so I think I have 5 minutes left, and I probably cannot talk about the last bullet in my talk. So the last bullet is, so how do we actually conduct regression? So I'll just raise the question to you, and hopefully we can talk more about this offline. Okay. So this is joint work with Chaba. And so as we have seen, regression works, right? So regression together with confidence ball and a bunch of analysis and this and that happens to work in a number of different RL settings. But one practical question is, usually by regression, I mean that I start with some representation, some feature of state action, and we want to have a target function, let's say phi, and then we run regression. But to make this actually work, we have to pick this target function. And if we think about deep RL, for example, one thing that people tend to do, but very efficient, is people tend to do, for example, pixel-to-pixel training. We can use a recurrent neural network to try to predict the next image of the game. But we all know that when we play games or when we try to control a complex system, it's not necessary that all fine details about the games, about the image, or about the robotics, about robots are necessary to predict. Okay, so we don't want to do pixel-to-pixel training because much of the quantities we're trying to predict are not relevant to solving the RL problem. And also, we don't want to try to tune our neural networks by rescaling and shifting the target and trying to normalize things to make sure that something converges. Okay, because this is going to be pretty computationally intensive. Okay. So one motivating example is mu0, so which is DeepMind's recent advance in solving computer games. So basically, this is an algorithm, which is a single algorithm, but can solve a wide collection of computer games with pretty good efficiency and generalization. And what happens is this algorithm doesn't have to know the rules of the game. The algorithm is going to learn the rules of the games and then plan by itself. And one central key idea is because the games vary, the algorithm is not going to do pixel-to-pixel training because pixels have different meanings in each game. But the algorithm is actually trying to predict quantities that are only relevant to control. So the algorithm only try to predict value functions and policies. Okay.
How do you make reward? Like, how do you define rewards in this game?
How do I define rewards?
Yeah.
If you win, it's one.
Winning is reward.
Okay, so you
Yeah.
just have reward.
Yeah, probability of winning, maximizing the probability of winning, which is the expectation of this reward. Okay. Okay, so I'm going to show you this slide and do not talk about the algorithm. So basically what happens is, the question we want to ask is, we want to do regression for online learning. But do we have to do regression to predict the entire raw state, or to predict a bunch of functions over the next state? The other question is, can we only try to do regression to predict the value function at the next state? Do you see the subtlety? Because value function is not something we know, right? Value function is something being learned by the algorithm. And if we want to do regression to predict value functions, there's something that's contradicting. Okay. So the short answer is actually yes. It is possible to do regression only using values to make RL work with provable regret. And it's actually not necessary to try to predict the entire raw next state or a large collection of functions over the raw next state. And I just want to show you the title. So it's possible to do exploration efficiently using value-targeted regression, but rather than raw state-targeted regression. And actually, this is provably efficient, although it is quite counterintuitive. And I won't have time to talk about these details, and we're happy to discuss these ideas with you offline. Thank you very much.